Let's continue in 1.1 and look at this example. So let's suppose we have an example, and this will be 1, 2, 3, 4. So this is 4 space, 1, 2, 3, 4, 4 space, and just some simple calculations just to do some little bit of work. Go and work that out real quick here, and then we'll move on to the next definition and concept. I went ahead and wrote it out. Here we go. So you can check your work. Didn't want to spend too much time on something like that. Okay, let's continue. So definition 1.1 on parallel vectors. So let's let V and W be not equal to 0. And VW excuse me, VW in Rn. And so you may have remembered how they're parallel. They're just scalar multiples of each other. So we just say V is parallel, you could write it out, but V is parallel to W if and only if V is equal to R times W. Okay, and then they talk, and then R is a real number. R is a scalar. It's usually reserved for scalars. If R is positive, it goes in the same direction. If R is negative, it's the opposite direction. Okay, so R, they just throw that in there. So R positive, same direction. R negative, I guess they'd probably say R not equal to 0 as well. Opposite direction. And so if you have your vector V, then we know vector W is this, that's what we mean by parallel, but it could be, longer like that or shorter. So we know that. We know how to do parallel vectors. And then we could do opposite direction. Let's just do it like this. That's good enough. And you could do opposite like this, and then maybe make that smaller. I think that's the same. I think that looks parallel. Okay, so that's if it's negative. Oh, and actually I meant to do this. So this direction and then that direction. It's hard to make them look parallel. Anyway, they're parallel. Okay, so that's what we mean by parallel vectors. Okay, so we know that. Okay, next, this one's pretty straightforward, obvious. Not obvious, but just what you've done. Let's do linear combination. That's actually something we're going to use a lot. So this is definition 1.3. This is called a linear combination. You've already actually seen this before. But this is defining it in Rn. And it'll be used throughout, really, the text, frankly. Okay, so given V1, the vectors V1 to V sub k, so V1, V2, V3 to V sub k in Rn, and the corresponding scalar multiples, so R1 to R sub k in R. This vector, so given that, the vector W equal to, basically, this vector, when it's a linear combination, it's a scalar plus the other vectors. So it's R1, V1 plus R2, V2, and I'll write it out like that, plus etc. 2 r sub k, v sub k, that is called a linear combination of those vectors. So it is called a linear combination of vectors v1 to v sub k with scalars or coefficients r1 to r sub k. Okay, so we will be defining different things, whether or not a vector is a linear combination of other vectors. So one of the, and I'll just to jump ahead briefly in case you've seen it, if you can write a vector as a linear combination of the other vectors, then they're linearly dependent. So linearly independence is going to have to do with whether or not you can write one vector as the other in terms of a linear combination, which we'll get to later, but just thought I'd throw that out there. It's going to use that quite a bit. Let's see, what's next? All right, so let's look at an example of that. Something we've seen. So every vector, so let's use I and j. Let's just do I and j again, because that's a linear combination. So here's a statement. Every vector, we'll use b in R2 can be expressed as a linear combination of I and j. I, and we'll do it in R2, and then j. So this we did all the time in Calc 3. So b, which is equal to b1 comma b2, basically you break it apart, right, is equal to b1 0 plus 0 b1. You probably did this before. You can factor out the b1. That becomes 1 0. Factor out the b2. That becomes 0 1. So that's b1 with, oops. So that's b1, and then that's I, plus b2j. Right, so this is I, and this is j. So it's a linear combination. So b is a linear combination of I and j. So that's true for every vector in R2. And so what the idea we're going to start looking at is that essentially linear combinations of I and j make up or consist of all of R2. So that's what we call forms a basis for R2, that I and j form what we call a basis. That's what we'll get to much later. But those are the concepts we're heading to. Okay, so on this note, let's define what's called the standard basis vectors. So, and we'll define a basis later, but so for, let's change back to white here. So for R2, or not R2, so for Rn, so for Rn, the rth, I know it sounds weird, the rth standard basis vector, we use E sub r, and basically it's zeros everywhere except the rth position. So it's zeros everywhere and then you have a 1, and then a bunch of zeros. And that's what we call the rth component. So the E represents that I and J. So instead of I, J, K, well, you run out of letters, right? So we use E to represent that. So E1 is basically I, and E2 is basically J. Depends on what dimension you're in, whether it's actually I or J. So what that means then, and let me just come over here so we go on a different page. So B, we can express a vector B, if that's B1, B2, etc., to B sub n. That can be expressed as a linear combination of E's, E sub I. So that would be B1, E1 plus B2, E2, etc. to Bn, En. So it's the sum of those that forms that linear combination. Okay. Let's go on to another theorem, property. So this is another theorem. This is not directly in the book, but I want to show you how you can use some of these properties. So this is properties of the additive identity. And additive inverse. Okay, so let's let U and V be in Rn. And then C will have a scalar. Then 1. If U plus V equals V, then we must have U equals 0. Then U must equal the 0 vector. So this is actually the uniqueness of additive identity. Is what we would say. 2, if U plus V is equal to 0, the 0 vector, then U must equal negative V. And that's basically the uniqueness of additive inverse. So, like if you have 4, negative 4, 2/3, negative 2/3. So it's only one opposite you get. It's like there isn't another one, essentially. 3, the scalar 0 times V is equal to the 0 vector. 4, C times 0. So any scalar times a 0 vector is the 0 vector. 5, if C times V equals the 0 vector, then C equals 0 or V equals the 0 vector. So you get a product of the vector times a constant. Either one of the other must be 0. And then 6, the opposite of the opposite is itself. That one's not trivial to prove, actually. Okay, so we're going to prove a 1 and 2. Okay, so proof of number 1. So first let's let U and v be in Rn, and c a real number, constant, scalar. Okay, so what you need to do when you do an if-then proof, so it says if this is true, then this must be true. So we're going to assume that this is true. And this is standard if-then proofs. So we want to first assume basically the hypothesis. So the assumptions are this, and this would be what you have to assume. Excuse me. So you assume u plus v is equal to v. Okay, and then we're going to start applying properties of addition and stuff like that. But we'll mostly apply theorem 1.1 properties. So the ones we're going to use. What am I doing here? It just got all weird, didn't it? Okay. We're going to mostly use 1.1 properties. So I instead of referring back and like that, I will just tell you which ones they are. Well, I probably have to refer back. Never mind. Okay, so here's our theorem. So let's assume that u plus v is v. Now, these are not really like obvious sometimes how to show these, because you can't use all those rules you normally like to use. So what you can do is you can add negative v on both sides. And I'll abbreviate that OBS sometimes later. So when you do that, you get u plus v plus negative v plus, oops, that's equals v plus negative v. Okay, so then v plus negative v must be what? So theorem 1.1 number 5, let's go, I'll have to go back. When I have a vector plus its opposite, it must be 0. So by theorem, let's try that again. By theorem 1.1 number 5, we end up getting u plus 0 equals 0. Now again, you can't use other stuff. You can't just drop the 0. Like we have a theorem that says if u plus 0 is equal to u. That's by theorem 1.1 number 4. So by theorem 1.1 number 4, we have that we have this. Let me change the color there. So this is equal to just u. So u must be 0, the 0 vector. And then it's been proved. That's what we wanted to show. That was the conclusion here. Okay, proof number 2 is next. Maybe try it on your own. Think about it. What's the first thing you're going to do? You're going to assume the hypothesis. So assume u plus v is equal to 0, the 0 vector. Okay, so if we do that, then what are we going to do? So if u plus v is a 0 vector, what are we trying to show? We're trying to show that u has to be negative v, like these have to be opposites of each other, right here. So what I'm going to use then, I'm going to use that 0 is equal to u plus negative u. So 0 is equal to u plus negative u by theorem 1.1 number 5. So the same as I just did above there, right? So I can rewrite 0 like that. So I can say then that u plus v is equal to 0 if and only if, I'll use this symbol for if and only if u plus v is equal to u, my pen's messing up, is equal to u plus negative u. All right, so now what I can do, I can add negative u on both sides. So if I do that, I say I get if and only if u plus v plus negative u is equal to u plus negative u plus negative u. Now I can commute these. So by commutative property, I can commute those, and I get that this is equal to u plus negative u, oops, and then plus v, and now let's put that back to 0. That's 0 plus negative u. But what is, actually, well, that's fine. Yeah, let's do it like this. Just commute those again. So u, no, that's right. I had it right the first time. So that is 0, right? So 0 plus negative u okay, so that's just commutative property. But what about this? That is 0, right, because of the theorem. So that's 0 plus v is equal to 0 plus negative u. So now we're applying, again, theorem 1.1 number 4. That says that 0 plus the v must be just v. 0 plus whatever's here must be just that negative u. So I get that this is if and only if v is equal to negative u, which is what we wanted to prove. So that's another uniqueness of the additive inverse. It basically shows it's unique, which it's not quite there for uniqueness. We'll have to do that a little later, but the rest of them are a little easier to prove. Maybe take a look at them. But this is how you have to prove stuff. You can't just assume you have cancellation and this stuff cancels out. You have to only use the theorems and properties that are given. Okay, that's it for chapter 1.1.